As has been our modus operandum from the beginning, our lecture slides are tied a little bit to the Young and Friedman text, but it's content that we could find in another textbook, like the OpenStax textbook, for example. If you're following along in Young and Friedman, this is chapter 28, and we're getting to answer now a question that we started asking before break. We talked about magnetism, and we really didn't say much about why magnetism is a thing. Like, where does it come from? We talked about its effects. You know, if you have a magnetic field, we talked about the effect of that field on a moving charge or on a magnetic dipole or a loop of current, which is another magnetic dipole, or, you know, the construction of a motor. We talked about the torque that a magnetic field exerts on a loop of current that is mounted on a particular axis, and that we can convert the electrical energy associated with running the current through the wire into the rotational mechanical energy of the rotating loop. And we talked about all the consequences of a magnetic field, and we agreed, I suppose, that you can get one if you have a magnet. If you have one of those, what did we call it? Magnesia rocks, right? If you've got one, then it makes a field. It has a field. It generates a magnetic field in its vicinity that does all that stuff we just talked about. But where does that magnetic field actually come from? We will address these objectives, or at least we're going to try to. At the end, we can look back and see how well we did. I'm not going to read them to you. You can read. I'm not going to insult you that way. A preview, in a certain sense, of the coming attractions, which was a joke about the previews at the movies, but was actually also a joke about attraction and repulsion and forces. And I didn't mean it that way at first, but it definitely, I think it landed in that spot. So that's a solid pun, and I'm keeping it. Here's an introduction, some kind of motivating question, which we've actually already asked. This is a enormous, you can see the people there in the picture for scale, an enormous coil that carries current, wound around and around and around and around. We call it a solenoid. And all right, we're going to use that for experimentation. What does its magnetic field look like? And why? What actually creates the magnetic field? In order to answer that question, I'd like to take a detour away from the Young and Friedman text. And I'd like to, I toyed with like we did with Gauss's law, just sharing the 6 ideas text with you and asking you to read it. But I thought maybe this time I would nutshell a little bit. To answer the question, what is the magnetic field of a solenoid and why? We have to go back. And we have to go back to the early 1800s. We're like pretty squarely 200 years ago. We have shown, and we've seen it happen, that a current carrying loop or a current carrying wire responds to the presence of an external magnetic field. And we looked at the pivot activity showing us that happened in real time. I mean, I guess not live, but in real time. A current carrying loop, particularly, responds to an external magnetic field as if it is a permanent magnet. And we looked at images side by side. One was a loop of current in a field, and we had field lines drawn, and there was an attractive force, and we looked at a bar magnet, and there was an attractive force, and the picture was the same, except for the fact that one of them was a loop and one of them was a bar magnet. A current carrying loop responds to a magnetic field as if it is a bar magnet. Okay, so you got 2 bar magnets and you set them next to each other, and the situation is one of relativity. If we look at this bar magnet from the point of view of this one, or we look at this one from the point of view of this one, it should be symmetric, because you all are looking at my 2 hands thinking this one is on the left, but I'm looking at it thinking that it's on the right. And there shouldn't be any change in the story. If I see this magnet on the right and you see it on the left, we're going to see the same outcome. So we could replace 2 bar magnets, but that first bullet is suggesting that we could replace one of them with a current carrying loop. But in order for that to be true, a current carrying loop has to behave just like a permanent magnet and possess a magnetic field all its own. Wouldn't it make sense if a current carrying loop responds to a magnetic field? Shouldn't it also create one? I mean, I would want that to be true. That has a nice symmetry to it. We are not alone in thinking that such a symmetric behavior would be nice, that these physical relationships, we see other symmetries, and we look at this and we say, yeah, I have some reason to suspect that maybe there's a symmetry here as well. And like I said, we're not alone. It is the winter of 1819, and Hans Christian Ørsted is offering a course in electrostatics and magnetism. But no one really knows anything about magnetism at this point. It's 1819. It's a qualitative survey of the behavior of compass needles and magnetic rocks. It's not quantitative at all. But Ørsted has this sense, this belief that there are symmetries, that the forces we observe and that we classify and we call them different things, that there's these forces are really just pieces of a whole, right? That there's some sort of unity to them all, which sounds a little bit fluffy. Um, but which isn't that crazy an idea anymore. We are discussing, right? Active research is ongoing right now, not in 1819, but in this year, uh, in the development of a grand unified theory to sort of synthesize all the known forces as one complete statement of, I guess, interactions. Um, it's not so silly an idea as it might sound, at least with the benefit of hindsight. It's not maybe so fluffy an idea. At the time, it was a belief and not an argument. Ørsted saw other symmetries and said, you know what? I think symmetry is a thing. I think there's some unity to all this. I can't prove it, but I suspect I really want it to be true that magnetism is some kind of variant of electricity, that they're the same. So he decided to try to prove it to his students, and he set up a wire with a current in it and initially oriented a compass needle perpendicular to that wire. And he turned on the current and nothing happened. And he was very embarrassed and ended class. And later he was sort of, oh man, I really wanted that to work. And he decided to try initially setting up the compass needle parallel to the wire. And the compass needle responded when the current was turned on. It clearly, sort of visibly deflected from its original orientation. That there is, in fact, a link between electricity and magnetism. So far, at least in 1819, this is a qualitative statement, but he publishes his finding in September of 1920. And this field of research explodes, just goes weeks only, a matter of weeks. Biot and Savart have quantitatively measured the field produced by a current. And we've talked a little bit about this picture before, but this is really where it sort of belongs historically. They were able to show experimentally that the field strength at points near the wire, a perpendicular distance r away. So here's the wire, and that's a perpendicular distance r. That x there, remember, indicates that the current in this case is flowing into the page away from our faces. They were able to show that the field strength, the degree of snap-to-ness that the compass needle evidences could maybe think of that, you know, if you've got the compass needle directed one way and you want it to be this way, how much time does it take to go from its initial orientation to that way? And as you go farther away from the wire, the field strength depends on inversely on that distance, that perpendicular distance from the wire. They were also able to show that it is directed in sort of circular arcs around the wire, which again is not news to us. To relate the direction, do these circles, do they go clockwise or counterclockwise? And as we're looking at them, they go clockwise. And the way to keep track of which way, which orientation the field produced by a wire of current is, I lost the grammar of that sentence. Anyway, the way to keep track of the orientation is with a right-hand rule, which is not really a surprise, given that we talked about right-hand rules before break. You know, we talked about that the force on a charge moving in a magnetic field is the charge Q times the cross product V cross B, which needed a right-hand rule. So it's not super shocking that we have another right-hand rule here. But here, this one's just sort of, there's no cross product attached to it, not really. Or maybe there is, but we don't need to think of it that way. Point your thumb in the direction of the current, your fingers curl around in the direction of the magnetic field. The magnetic field whose magnitude, whose strength varies inversely with distance from the wire. Now, the next unit, the next sort of topic area that we're covering after today is electromagnetic induction. After Ørsted's publication, the most significant development in the study of magnetism in 200 years. It was 1600 when the previous sort of treatise on magnetic behavior was published. 200 years. In a matter of 12 years, Michael Faraday has published an extensive study of electromagnetic induction. And something about that word, electromagnetic, does sort of give a nod to Ørsted's idea that there is an intimate connection between them, electricity and magnetism. I know, though, from our work in previous topics, that when we talk about a current flowing into the page in the wire in the direction indicated, that what we really are talking about is the motion of individual charges, which makes me wonder whether, if the current represented in this figure were the motion of a single charge. Well, wait, I psyched myself out just there. I said charge and I panicked. And I said, no, we're not talking about charges. We're talking about magnets. That's true. And there are no magnetic charges, right? Every magnet, every magnetic field is the result of a magnetic dipole that we saw that last time. But here we're back to current. We're back to electric current as sort of constituted by the motion of individual charges. So we're back to this idea of charges in motion. Again, we talked about this before break. Force equals QV cross B. If it's not Ving, then there's no force. If there's no velocity through the field, then there is no force. A charged particle at rest in a magnetic field does not experience any magnetic force. Okay. So can we talk about the magnetic field that would be produced by a single moving charge? Or by charges that are in an electrostatic situation that are then moved manually. It's a little bit more than 12 years, but in 1875, Henry Rowland conducts an experiment which took a little bit of doing. There were really, really high charge magnitudes involved, and it took some effort to shield the compass electrostatically from those effects. But Henry was able to show that the magnetic field produced, you got a disk and you got a charge on the outer edge, and you take the disk and you put it on a turntable and you spin it. Those are moving charges. They're stuck on the edge of that disk, and the disk is moving, so the charges are too. And we're able to show here in 1875 that there is a magnetic field produced which is identical to the one produced by an equivalent current flowing in a wire loop. We have two pieces of information now. We have this empirical evidence that charges moved creates a magnetic field, and we have this other evidence that a current creates a magnetic field, and a current is comprised of moving charges. Okay, let's put this together. Here's my reasoning. This is how I was thinking about it as I was thinking about this content. Way back, several topics ago, we found the electric field due to at least in the limit of an infinitely long line of charge. That field had a magnitude that varied inversely with perpendicular distance from the wire, or not the wire, perpendicular distance from the line of charge. But the infinitesimal electric fields at the point that we were interested in evaluating the electric field, the infinitesimal electric fields that we integrated, that we summed over the length of the wire to sort of accumulate the total electric field at point P. Those individual fields depended on the square of the distance between the infinitesimal charge we were considering along the line of charge, the square of the distance between that charge and the point. So, okay. So we had a line of charge. Each little bit of charge contributes an electric field according to 1 over r squared. And we summed that all over the line of charge, and we ended up with a result that varied like 1 over r. Just a second ago, we quantitatively measured the magnetic field due to a line of current varying like 1 over r. A line of current like infinitesimal charges moving with the drift velocity. Could we reason by analogy? We're just gonna, go take a leaf out of Ørsted's book and say this should be there. It feels like there's a symmetry here, so I'm just gonna argue that there is. Could we imagine like a Coulomb's law for magnetic fields? A charge moving somewhere in some direction, the direction of the drift velocity, a charge moving that way, a current up. Right-hand rule creates a magnetic field. If the wire is here, if this is the wire, I use my right hand, I point my thumb in the direction of the current, and my fingers point into the camera. Away from my face, towards your face. So we talk about in a bit of that current, and we look over here, a bit of that current right here at this gold spot along the pen. And we do that thing, and then the magnetic field here, we're some distance away, but we have to integrate all of the contributions because we're different distances away from all of those moving charges. Isn't that the same thing that we did for the electric field calculation? Doesn't that mean that if we're going to get the same result, a dependence 1 over r, shouldn't we have started with an original dependence 1 over r squared? You want to talk about current? Okay, I hear charge and velocity, and I think r 1 over r squared. And this is an equation that does that, that says exactly that. Apart from the cross product, I'm going to argue that this looks a lot like Coulomb's law. Field equals something 4 pi, some kind of constant, something, some Greek letter sub-zero. For Coulomb's law, it was epsilon, but for, well, I want to use a different constant. Maybe they're equal, I don't know, but I want to use a different one just in case. Magnetic constant, mu, I don't know, why not? We've seen the letter mu come up in the magnetic context before. We need to know how much charge is moving. We need to know how fast it's moving. and there needs to be some way to get the right-handedness of that interaction. If the charge is moving up, the field points perpendicular to that. That's a cross product. That's a cross product. But how do you get perpendicularity built into an expression like this? Well, you use a cross product. That's what we had to do when we were talking about torque. That's what we had to do back in 231 when we were talking about, I don't know, angular velocity and tangential velocity. You want perpendicularity? I can express it with a cross product. And we do have our 1 over r squared dependence. It looks a little bit like we're taking r and dividing by r squared so that it would have only sort of a net 1 over r. But this doesn't have the magnitude of r. It's got a hat. It's a unit vector. Its only job is to show us the direction so that we can use the cross product, essentially. And the r squared dependence is explicitly there in the denominator. What do you think? Have I sold you on the fact that there are good reasons why the magnetic field of a moving charge should look this way? It's one of the reasons I was, I was working on this for a couple days, trying to figure out a good order in which to present certain things. This particular topic has a weird circularity to it. We need this in order to sort of justify the analogy to Gauss's law. There is a sort of simpler, more elegant way to express the relationship between moving charges or currents and magnetic field. And we'll talk about it eventually, but in order to justify that it's a thing that works, we need to have this answer we need to have this relationship to begin with so that the other thing, is believable. And then we could use the other thing to prove this, but that's a weird kind of, so it was these first slides, what I tried to do was provide some motivation. Why might we look at this relationship and trust it? Can we connect some intuition to this relationship? We could use these ideas of a current density of charge carriers. We could define a current as J times A, the cross-sectional area, a vector J in the direction of the current. We could use our definitions of current density in terms of the number density of charge carriers, the charge on each charge carrier, and the drift velocity. And we could, wait a minute, what did I just say? The charge on each charge carrier and the drift velocity. That we can connect to current density, and current density we can connect back to current, which means there's a version of this that we can write for current just as well as charge. We have defined current as a scalar quantity, which means in order to get the cross product to work here, we need a length vector that points in the direction of the flowing current. It's parallel to the current density vector is really what's going on. But if we make that choice, then we can talk about the current flowing in a small section of wire, I guess, dl. It needs to be small. We've got this written in infinitesimal form. It needs to be small so that the current is appreciably constant. It can't vary over the size of the wire that we're talking about. And it needs to be short enough that it is arguably straight. Otherwise, so that DL points only in one direction. If the DL actually had to curve, then the cross product with the position vector wouldn't behave right. So we imagine little steps in the direction of the current. And if we wanted to find the total field of the total magnetic field created by a particular geometry of current, we could add these up. We could integrate these infinitesimal magnetic fields. Okay. It's a bit of a non sequitur, but I left this slide here. There really wasn't a better spot to put it, and I thought it was interesting. The Earth has a magnetic field. Otherwise, we wouldn't have been so excited when we found those magnesia rocks and then realized that they always point that way. Why does it have a magnetic field? And it has to do with a current, a flow of molten material in the core. Jupiter has a much, much stronger magnetic field because it has a much more rapid rotation. So if we look back at this formula, we've got charges moving faster, increase the magnitude of V, we're going to end up increasing the magnitude of B. Increase the current density, Jupiter's bigger, we're going to increase the infinitesimal magnetic field, and we can increase the overall magnetic field. really this slide, now that I'm thinking about it, this slide should probably go towards the end when we're asking our question, why do permanent magnets behave like permanent magnets? Because we're starting to tell a story about electric current, and those permanent magnets that I have attached to the whiteboard that we were, I don't know why I'm pointing over here. You don't know what I'm pointing at, but the magnets that we were looking at last time. Where's the electricity involved? You know, if a magnetic field is created by a current, well, where's the current? And this slide actually gives us a little bit of foreshadowing. Um, I don't know. So, like I said, I can't figure out where to put this slide. I could, it's here, so here it is.